Welcome back, everyone. I am absolutely thrilled to have you here for another strategy session. Today, we are taking on a completely new approach to mastering your exams. We're stepping into the shoes of the paleontologist. What does that mean? It means when you look at a massive, intimidating Cambridge mathematics question, you don't panic. You dig through the fossil layers, the different parts of the question, and you carefully reconstruct the full, perfect answer to get maximum marks. Whether you are studying syllabus 0580, 0606, 4024, 4037, or 4040, this strategy is your ultimate blueprint. Today's dig site, Indices and Algebra. To show you how this works, we're going to look at two typical students. First, there's Alex. Alex is the overloader. Faced with an index problem, Alex just vomits raw mathematics facts onto the page, completely ignoring the analysis. Then there's Sam. Sam rushes. Sam completely misses the crucial command words hidden in the question requirements and loses silly marks. We are going to look at their flawed answers, break out the red pen, and show you exactly how to transform your approach. Let's dive into this.
Right, let's set up the core challenge of today's excavation. Look at this classic high-mark Cambridge question style. How do you solve for x when x is the exponent itself? This is a scenario that separates the top-tier candidates from the rest. We usually think of x as a base number, sitting comfortably on the ground, like 2x equals 10. Easy, right? But what happens when x climbs up into the corner and becomes the power? When Alex sees a question like this, Alex just starts writing out every single rule of indices without actually answering the specific question. Zero analysis. And Sam? Sam sees a power, panics, tries to divide the big numbers, completely ignoring the command word, which is usually solve or evaluate, not just simplify. To figure out how to avoid both of these traps, we are going to take a journey from the basic numerical rules you likely already know, all the way up to complex algebraic puzzles. We're going to reconstruct the perfect answer layer by layer.
Here is our cognitive roadmap for the explainer, our excavation plan, if you will. We'll start by dusting off the rules of indices. Then we'll apply those rules to simplifying expressions. After that, we'll crack the code on solving exponential equations. And finally, we will reconstruct the entire dinosaur by graphing exponential growth. Knowing this exact progression is absolutely crucial to anticipating what the examiner is going to ask you next. Okay, let's break ground with Section 1, Rules of Indices, from numbers to algebra. Now, as we reveal our exam strategy, I need to introduce you to the PEEL framework. Point, evidence, explanation, link. Top students use this to structure their mathematical thinking, but before we can use the framework, we need our basic tools. The biggest secret to algebraic indices is that you don't actually need to learn net new rules. The rules you already know for plain old numbers apply directly to algebraic terms. And this side-by-side comparison brilliantly illustrates exactly what I mean. Take multiplication. When you multiply 2 to the power of 3 by 2 to the power of 4, the rule is to simply add the little numbers to get 2 to the power of 7. The exact same logic applies to algebra. A to the power of m times a to the power of n is just a to the power of m plus n. Division, you just subtract the indices. And when you have a power raised to another power, like 5 squared all raised to the power of 3, you multiply those indices together to get 5 to the power of 6. The algebraic rule on the right is literally just a generalized version of the numeric rule on the left. It's the exact same machinery. When Sam rushes through an exam, Sam often mixes up addition and multiplication here. Don't be like Sam. Slow down and decode the operation. Let's dig a little deeper into the special cases. But hey, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the dig site. You need to memorize these base-level transformations because examiners love using them as trick questions. First up, anything to the power of 0 is 1. It doesn't matter if it's 5, 100, or a, it's 1. A negative index, like a to the power of negative m, is just a fraction in disguise. It's 1 over a to the power of m. And fractional indices, those are roots. A to the power of 1 over n is the nth root of a. If the fraction is m over n, it's the nth root of a to the power of m. Alex often tries to write out massive paragraphs explaining these concepts on the exam paper, but the examiner doesn't want an essay. They want you to recognize the disguise and immediately transform the term. Once you spot these disguised fossils, the algebra becomes so much easier. Moving on to Section 2, Simplifying Algebraic Expressions. This is where we see the transformation happen. Now we are going to take the theory we just looked at and use it to clean up some messy algebra. We are going to watch the red pen marks transform into green check marks. Here is a great example. The command word here is simplify. We need to simplify 3p to the power of 5 times p cubed. Let's use our mathematics success blueprint. Step 1 is to visually break it apart. Identify your big numbers, the coefficients, and your bases with indices. Here, we just have a 3, and then we have our p terms. Step 2, we apply our algebraic multiplication rule to the bases. Since we are multiplying p to the 5th by p to the 3rd, we simply add those indices. 5 plus 3 is 8. Step 3, put it all back together. The 3 stays right where it is, and our final combined result is 3p to the power of 8. When Alex answers this, Alex writes 3p to the 15th, incorrectly multiplying the indices. But because we paused to identify the command word and methodically applied the rules, we secure the full marks. Handle the big numbers normally and use the index rules for the little numbers. Let's look at something slightly more complex, in a place where a lot of students lose marks. We are simplifying the expression 5m squared n cubed, and all of that is inside parentheses, squared. So the crucial point here, the absolute golden rule, is that this outside power applies to every single part of the term inside the bracket. This is where Sam always trips up by rushing. Sam will square the letters, but forget the number 5 entirely. Step 1, apply that square to the coefficient first. 5 squared is 25. Step 2, apply the power of a power rule to the m term. We multiply the indices. 2 times 2 is 4, giving us m to the 4th. Step 3, do the exact same for n. Multiply the 3 by 2 to get n to the 6th. Step 4 is our final beautiful result. 25m to the 4th, n to the 6th. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Believe me, you don't want to miss the techniques we are dropping. All right, let's jump right into Section 3, Solving Exponential Equations. Welcome to the interactive workshop phase of our explainer. This is what I like to call the puzzle phase of the syllabus, answering the big question we asked at the very beginning. Let's do a quick 60-second data scan challenge. When you scan an exam paper, what tells you that you're dealing with an exponential equation? The definition is key. These are equations that involve indices as unknowns. The x isn't on the ground anymore, it's up in the air. When you see that floating x, your brain should immediately trigger a specific strategy. You shouldn't be trying to divide or factorize normally. You need the index toolkit. Time's up on the scan. Let's see this in action. Let's tackle challenge 2. Find the flaw. Look at this equation. 32 to the power of x equals 2. Now, Sam tried this in a mock exam and immediately wrote x equals 2 divided by 32. Sam lost all the marks. Why? Because you cannot divide a base by a base when the unknown is an exponent. The examiner commentary here is brutal. They want you to use a strategy called finding a common base. Step 1. Look at the number 32. Can we write 32 as a power of 2? Yes. 32 is exactly 2 to the power of 5. Step 2. Substitute that back into the equation. Now we have 2 to the power of 5, all to the power of x, equals 2 to the power of 1. Step 3. Simplify using the power rule we just practiced. Multiply 5 and x, giving us 2 to the power of 5x equals 2 to the power of 1. Now look at what we've reconstructed. Both sides have a perfectly matched base of 2. For this equation to be mathematically true, the little numbers must be equal to each other. Step 4, drop the bases entirely and equate the indices. 5x equals 1. Divide by 5 and x equals 1/5. Flaw found. Puzzle solved. Mark secured. Okay, challenge 3, speed writing. You have a 30-second mental timer right now to structure your perfect Peel paragraph for solving 125 to the power of x equals 5. Go. Step 1, point. Identify the relationship. 125 is 5 to the power of 3. Step 2, evidence. Set up the new equation. 5 to the power of 3, all raised to x, equals 5 to the power of 1. That simplifies to 5 to the power of 3x equals 5 to the power of 1. Step 3, explanation. Ignore the bases of 5 since they match perfectly. Just equate the new indices. 3x equals 1. Step 4, link. Solve for the final answer. Divide by 3 and x equals 1/3. Boom. 30 seconds. The secret key is always finding that common mathematical ground. If you write out those precise steps, the examiner literally has no choice but to give you full marks.
Finally, we reach Section 4, Graphing Exponential Growth, the top layer of our excavation.
It is time to take these abstract equations out of the math lab and drop them into a visual, real-world scenario.
The command words here will often be model or evaluate. Here is a classic real-world model directly from our source material. Imagine a dripping tap slowly filling a container. The water level, which we'll call L in centimeters, is modeled by the equation L equals 2 to the power of t minus 1, and t is the time in hours. Look closely. Notice where the t is? It's an exponent. This equation describes an exponential rate of change over time. When Alex reads a massive word problem like this, Alex freezes up, but you won't, because you know how to extract the core data trend.
Let's execute the strategy. What is the water level after 3 hours? We take our extracted equation, L equals 2 to the power of t minus 1, and we literally just plug in 3 for t. 2 to the power of 3 is 8, and 8 minus 1 is 7. So, after exactly 3 hours, the water level is 7 centimeters. It's a highly concrete, very visual application of the formula we've been reconstructing all day.
But what if you can't easily find a common base algebraically? Say Cambridge asks you to solve 4 to the power of x equals 30. 30 is in a neat power of 4. This is where we introduce the final piece of our answering system, graphing. Here is how you guarantee those final marks. First, you plot points and draw the smooth curve for y equals 4 to the power of x. Then, you go to your y-axis and locate your target value, which is 30. You take a ruler, do not freehand this, and draw a horizontal line straight across until it hits your curve. From that exact intersection point, you draw a vertical line straight down to the x-axis. Whatever number you hit on the x-axis is your approximate solution for x. It's an incredibly powerful visual method. So let's recap the 3 rules of our mathematics success blueprint that guarantee top marks. Rule 1, command word decoding. Always know if you're simplifying, solving, or modeling. Rule 2, Peel framework application. Structure your steps logically, finding the common base. Rule 3, time management matrix. Don't rush like Sam, and don't overwrite like Alex. Get in, reconstruct the answer, and get out.
Which leaves us with one final, provocative thought to ponder. Let's go back to our dripping tab, where L equals 2 to the power of t minus 1. Using the common base strategy and the exact rules of indices we've covered today, can you calculate the exact time it takes for that water level to hit 31 centimeters? Think about setting up the equation 31 equals 2 to the power of t minus 1. If you add 1 to both sides, you get 32 equals 2 to the power of t. Does 32 look familiar? I bet you can solve that puzzle right now. Listen, students who implement these exact mathematics strategies see an average improvement of 2 full grade boundaries, but that only happens if you practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. See you in the next one.